I can start away, whatever.
We can continue like.
Yeah. Let's continue before people get lost on the way to the kitchen.
Yeah, so the next presenter is Sascha Brune from GFZ Potsdam. As you already heard, he's also a tectonic guy compared to the geochemist here in the audience. So, Sascha.
Yeah, thanks a lot, Arthur. Can you see the screen? Is everything okay?
Yes.
Yeah, so thanks for the invitation, and of course, speaking after Sabine is always fun. And this was a great introduction from Sabine of what you can learn from all these components of the carbon cycle. And now I will just build on this and focus only on one of these dots that he had on the map in the end, so continental rifting. But before I start, I'll give you a quick introduction to continental rifting and also to what I'm doing in GFZ in Potsdam. So since a year, I've been heading the geodynamic modeling section, and we run geodynamic models here on all kinds of subjects, on continental rifts and normal faults, on mantle convection, but also on earthquakes. So this is the subduction zone and the velocities that are building up over long times and then that are released during an earthquake. And we also run tsunami models. So this is everything geodynamic forward modeling. So this is kind of the stuff that we do. These are the people that are involved right now, but there are a few more coming soon. Right, so continental rifting. This is about breaking plates, about forming normal faults, like these beautiful exposed normal faults in Ethiopia. And there are several generations of these faults. And I would like to focus really on these faults. That's why I give a few minutes in the beginning of how they form and how they evolve. So this is a very simplified schematic of a continental rift inspired by East Africa from Cindy Ebinger, who has been working in East Africa for many decades. They initiate due to stretching of the crust and of the mantle lithosphere. So this stretching is taken up by normal faults at the surface and to some degree by dike intrusions. And the further we go forward in the evolution of the rift, the more of this extension is taken up by magmatism and less by normal faults. And that's why we have this transition from continental rifting to seafloor spreading, where in the end, a large component of the extension is taken up by dike intrusions at the mid-ocean ridge, but also some normal faults in the end. An important thing about continental rifts is they're in a constructive plate boundary. So you create new surface at the surface of the Earth, which makes it very nice because you can reconstruct them nicely back in time. You can see what's happening at a destructive plate boundary, at a subduction zone, for instance. You destroy information and it's hard to reconstruct them. And you have to do really plate circuits to get a handle on subduction velocities. And another important thing about continental rifts is that they are intrinsically transient. There's not an easy steady state for continental rifts because they live on thinning the lithosphere, on thinning the crust, and that's why there's always a progression. You thin it a bit more and then you come to another state. And this state can be represented by basinward localization of the faults. And this is shown in this little animation of a model that I ran yesterday, in fact. And this is showing the transition from continental rifting, where we have border faults, big border faults like the ones that I showed in the image from Ethiopia, associated sedimentation, but the sedimentation could also be lava flows if you want. And then localization towards the basin of the sedimentary basin, abandonment of the border faults, and more activity here in the center of the rift. So the focus changes, and all these structures, they are retained, and you can visualize them and look at them through the seismic data at rifted margins and assess the tectonic evolution of these rifts and how they evolve through time. Yeah. So this is a rather complex model. I don't go too much into details, but we can get surprising structures here and asymmetries that just emerge out of the interaction between localization processes, sedimentation, and upwelling of the asthenosphere. And if you think of these rifts in terms of the carbon cycle, then you melt material, especially where it's hot and where you have a lot of carbon. This helps with melting. So in the beginning of rifting, you might have very deep melts and very CO2 rich melts. And the further you progress towards the floor spreading, your melting will be more dominated by asthenospheric melting, and you produce more warp type basalts. All right, so this is a brief introduction. The talk will be split up in 3 parts: methods, analysis, and future. So I start with the methods, and there I focus a bit on carbon cycle models and on how I analyzed tectonic reconstructions, the ones that Sabine showed you before. So in carbon cycle models, they try to capture the complexity of the interaction between all the reservoirs at the surface. So most of these carbon cycle models focus on the shallow carbon cycle, which involves the biosphere, including us humans, the marine component, the atmosphere component, and the soil, and to some degree the fossil carbon reservoirs. And every arrow that you see here is one component that can be represented in a carbon cycle model in these box models. So they can be very complex. But if you go deeper in time, if you look at it not at the short-term time scale, and there are many short-term time scales in there, but if you look at it from the geological time scale, then many of these arrows are actually so fast, they are acting so quickly that you can simplify things again, which is a good thing, because then you can say certain components, for instance, the atmosphere and the ocean on the geological time scale, they are equilibrated. And so in these long-term carbon cycle models, we don't have to explicitly account for feedback between ocean and atmosphere. But what we have to account for is what's visualized here with the volcano. This is the CO2 that's coming from deep box, from the deep compartments of the Earth. This is my geochemistry slide. Yeah, there's similar to Sabine. This is not my expertise, but I learned that you can represent this complexity of the interactions at the surface. You can capture the essence of that in very simple formulas. So this is the very simple formula for photosynthesis and burial. Of course, there are many sub-steps in between these small arrows, but what photosynthesis is doing, you take CO2, you take HO2, you produce organic matter and oxygen. And if you decompose the organic matter here, then you just go in the other way. So this is one component. This is one simplified way of describing all these little arrows that you saw on the back. And then there's carbonate formation from silicate. So this is where weathering comes in. You take silicate rocks, you weather them under the presence of CO2. You transport the carbon, so the calcium and the magnesium ions to the ocean, where they precipitate and generate. So this silicon oxygen, this is produced during the weathering, and the carbonates are produced during the precipitation in the oceans. And if you go the other way around, then you can decompose your carbonates and again generate CO2. And this simplified version of the carbon cycle is implemented in these geological time carbon cycle models. And so these are the arrows here. This is the simplified version of the diagram from before. And there they compute the change of the carbon mass at the surface, so to say in the surface system, or you can think of it as the atmosphere. And all these arrows can be represented as fluxes. So for instance, this flux here, this is due to weathering of carbonate rocks. This is weathering of organic material. And then these are your sources of CO2. And you have your sink. This is where you bury organic material or where you bury carbonates. And if you phrase it this way, then you get a very simple set of equations that you have to feed with data. And this is done in this first generation carbon cycle models, GeoCarbSolve, which derived from Berner in the late 80s and then was taken up by Dana Royer later on. And this captures this set of arrows that you've seen before and feeds them with data that we have. So strontium isotopes, carbon isotopes, paleogeography, these are all parameters of this box model. Seafloor creation rate is the one that represents tectonic contributions, and it's only one, and this is a big shortcoming of these kind of models, I think, and Sabine will probably agree, because there are many components of the tectonics contribution to the carbon cycle. And then there are some other scalar parameters that I just mentioned, some of them to show the breadth of the disciplines that are integrated into these carbon cycle models. So we have some petrological aspects, activation energy for dissolution of silicates, weathering efficiency of volcanic and non-volcanic rocks, but also biological components like the presence of trees, erosion efficiency of gymnosperms versus angiosperms. This is one that I like particularly. And this is a classical image from an output from these carbon cycle models from GeoCarb-SOV that shows one particular feature. So this is atmospheric CO2 over time, and the dashed line is the atmospheric O2 over time. And what they highlight here is the origin of forests. So this is affecting one of these parameters, this presence of trees. And by having trees, you get more photosynthesis. So you reduce CO2 by that and increase your O2. And this is the decrease of CO2 and the increase of O2. But at the same time, you change your weathering efficiency, because the roots of the trees, they are more capable of weathering silicate rocks. And that's why you have two components here, one from photosynthesis, one from weathering. And this generated this drawdown in CO2 at 350 million years ago. And shortly after, you have a glaciation, which can be explained by kind of the presence of the trees. It's a very simplified explanation, but it's catchy. That's why I'm mentioning it. So CO2 goes down, it gets colder, less greenhouse effect, and that's why you get a glaciation. And at the same time, you have high O2 levels, which means that the metabolism of the insects can work better, and that's why they can get larger. And so you have this correlation between tectonics, forests, insects, and glaciation. Well, there's no tectonics in there, but tectonic comes later. Let's switch to tectonics. So this was for the carbon cycle models, and now I come to the tectonic reconstructions, and I won't delve too much into that because Sabine showed a lot of the details already, but they integrate all kinds of observations that we have right now. Magnetic stripes, geological data at the continents, seafloor fabrics, here these fracture zones that are supposed to be parallel to plate motions, gravity anomalies that let you map these fracture zones and see some other interesting features. And G-Plates is this software that Sabine mentioned. You can just download it and scroll through time through this little ruler here. And when you do that, you can take the continent-ocean boundary. So this is where the continent stops and the ocean begins. And the coastlines, there are nice data sets. And this is essentially output from the desktop version of G-Plate. So I reconstructed the continents back to where they were 200 million years ago. And this is all qualitatively. You can look at it and everything's fine. But the majority of my talk will be about quantitative analysis. And for that, I used a Python interface that Medicine East used as well. So PyGplates. Now you can script things, and you don't have to look at it at the desktop or at the monitor and maybe measure the length of subduction zones at the monitor, but you can quantitatively script things and get data out. And now focusing on continental rifts, I want to get rift length. And I do that this way, that I zoom in here, and you see that the continent-ocean boundaries here of North America and Africa, they overlap. And if they overlap, that means that we have rigid plates. So an overlap between these rigid plates means that there was a production of surface, yeah, because rifts are constructive plate boundaries. We produce new surface. And this overlap here, this is the amount of surface that was generated during rifting between North America and Africa. And if I reconstruct the velocities of North America relative to Africa, I can also say when this overlap was created, when this surface was created. And this is what is an active rift. So this is the way how I can extract from the plate reconstructions whether a rift was active or already not active anymore. Right, so, and this is what I'm doing. And then I link that to a carbon cycle in the following way. So before we've seen all these interactions at the surface, but we want to focus on the tectonic contributions here. And before I go into the details, I want to mention how important they are. So what Sabine showed as this C in the DCO that was kept, this is the distribution of carbon on Earth. So we have the atmosphere. This is 0.0000115% of the entire carbon on the Earth. This is tiny, and every change that you can add to the atmosphere adds to the greenhouse effect and adds to the climate change. The biggest majority of the carbon on the shallow Earth is in the continents. It's 1.5%. It's still not very much. Then we have the mantle with about 10%, and we have the core of 19%. So this is the entire budget on Earth. And so you can imagine that if you have a mantle source, be it in the continents or in the deep mantle, and you release this carbon to the atmosphere, every process that releases this carbon can have a big impact on the atmospheric CO2 and on climate change. So the traditional view was that we have places like volcanoes where we release a lot of CO2 to the atmosphere. And that's why people were focusing on volcanic chains. And the biggest volcanic chains that we have on Earth are the mid-ocean ridges. That's why in the geocarb solve models, they have this component of seafloor creation rate and mid-ocean ridge volume fluxes, essentially. And people have been doing that in recent times as well. Volcanism at mid-ocean ridges, at subduction zones, and at continental arcs. So these are all the places where we have volcanoes. And there the carbon is taken up from the melt at depth, and then it's transported to the surface and then released close to the volcanoes. But in recent times, it became more and more apparent that the CO2 is also released along faults and not only along volcanoes. This can be because melts are trapped at depth and they degas at depth, and then the volatiles move along the faults to the surface. And there doesn't have to be a volcanic expression at the surface, but you can still have CO2 release at the surface. And this is interesting because the amount of volatiles and the amount of fluids that you have along these faults, they also help to keep the faults active. Because if you have more fluid pressure in the pores, this reduces the effective friction coefficient, and this makes it easier to create a fault or to maintain a fault. So there's a two-way positive feedback between the presence of fluids and volatiles and faulting. This makes faults a very likely location for get fluid flow at the surface and CO2 release at the surface as well. And this has been documented in several places. So in the East African rift, we know that there is an occurrence of CO2 flux along rift faults, both in the eastern branch and the western branch, in the Basin and Range, in the Ega rift, Rio Grande rift. So these are all currently active rifts. Central Italy, I see that Carlo is there. Hello. And in New Zealand, there's also documented CO2 fluxes that have been extrapolated to a large area so that I can actually use them in this talk. I want to focus on one particular study that where they measured CO2 flux in East Africa, particularly in this southern area of the Kenya Rift and in Tanzania. And so if we zoom into that area, this is a nice view of the rift basin from the top. Here are the border faults that you've also seen in the animations before. And this is an asymmetric rift basin where this side is flexed downwards, and this flexure is taken up at the surface by this set of normal faults that are really densely spaced here. And if we zoom even closer in, then we find that along these normal faults, we can have springs. And if we measure CO2 flux CO2 soil flux, so with gas accumulation chambers that you have to carry around and put on the ground and measure how much CO2 is coming out, then you can get these little red dots. And they show how much CO2 is coming out, how much grams per square meter per day over this distance. And there's a correlation between the faults at depth and the flux of CO2 at the surface. And also you see that in terms of the springs down here. And now what they did, which is a bit, I would say, questionable, because this is a huge extrapolation now. But what they did is they say, this is our area. We measured a few cross sections here, and we find that there is, if we extrapolate to our area, we find that there is 4 megatons per year of CO2 coming out of this particular basin. And then if we scale this up, that means that 1,000 kilometers of rifts release 20 megatons per year CO2. Or if we scale it up to the entire East African rift, then we get about 71 megatons per year, plus minus 33. And this compared to to what we think comes out of the mid-ocean ridges is essentially the same ballpark. So this was the argument that rifts might be a previously underrepresented tectonic feature of the carbon cycle. And so this is where I step in now, and I say, well, how did rift length evolve through time, and how does it correlate with paleoatmospheric CO2? And for that, I go back to my tectonic reconstructions. I say, this is a rift. I can quantify how long it was, and I can do that over time. So this is these red dots. They are the rifts from the reconstructions, and they are mostly occurring along the plate boundaries that are mapped and that are included in the plate reconstruction. But we also know that there are rifts that are not included in the reconstruction yet, either because they are very small or they did not really make it to a big plate boundary that you can put in the reconstruction, or because they are just not in there yet. So, and these are the dots here that I took from a tectonic compilation of rifts from Schengen and Natal. So now I can look at how the length of continental rift system evolves through time, and you see that in the Cretaceous we have the breakup of Pangaea. We have the breakup between South America and Africa. So this is a long, very long rift system here. We have Australia separating from Antarctica with a very long rift system. We have Greenland rifting from North America and then away from Europe. We have rifts in Southeast Asia and in the Basin and Range. And then finally the East African rift. And so if I condense everything into one plot, I show global rift length in thousands of kilometers over time. And these are the individual rift systems. The colored ones are the ones from the reconstruction, and here are the names. These are the ones that are included in the reconstruction. And the gray ones are the ones from the geological record that I added on top of the ones that we know are in the reconstructions already. And if you say, I don't really believe in these tectonic reconstructions, they are just making things up, you are more a hardcore geologist, then this is what comes out of the geological record only. So this is a second data set that is to some degree independent of the reconstructions. But what both of them show is that we have a peak here in the Cretaceous and we have a peak here in the late Cenozoic. Yeah? So this is evident in both of them. And if I interpolate over both data sets in 10 million year intervals to just get rid of the small spikes, then this is the signals. L1 is the one where I include geological reconstruction and plate reconstruction, and blue is only the geological database. And so we have a Mesozoic rift pulse that is associated with the breakup of Pangaea, and we have a Cenozoic rift pulse that is associated with renewed rift activity in East Africa, in Western US, in Southeast Asia. And now I correlate this with CO2 release. I take the measurements from these really sparse locations that we have, and this is a point that I'll look into further later on. And I simply say, if I have thousands of kilometers of rift lengths, then this is the amount of CO2 that I get. Yeah, this is as simple as that. And then I can compare that to the CO2 content of the atmosphere that we get from paleo CO2 reconstructions. And here I have a little excursion to plant biology. So where do we know from the CO2 200 million years ago? And this is, I think, fascinating that this is actually doable. So I'll invest 3 slides and just to refresh you from all this tectonic stuff. So these are stomata. This is how the plants breathe. These are the pores through which the plants breathe. They take up CO2, they release O2, and you can look at them on a microscope, or if you just plug a leaf from a tree, you can actually see them. And now plants are clever. If there's a high atmospheric CO2, they want to be energy efficient, so they grow less stomata. And if you have low atmospheric CO2, they grow more stomata. We know that by just going along a mountain range, where if you go higher up, there's less O2, and you take the same plant species, then you can see this increase in stomata density. And now comes the great part. You can take fossilized reefs and you polish the surface of these fossilized reefs, and then you see the stomata here. So if you have a good idea about the paleo altitude where these leaves were growing, where these plants were growing, then you can recompute the paleo CO2 content. And particularly well, this works for plant species that did not evolve that much over time, for instance, for ginkgo families. And so now every dot that you see down here is one of these measurements. There are also other paleo CO2 proxies. There are several other ones, some of them involving plants and biosphere, and others are more soils or non-biosphere related. And if you average over these data sets here, then you get well, this broad line here, which shows a high Cenozoic CO2 content of the atmosphere. Then we have a low in the late Cretaceous and early Cenozoic, and a high during the Mesozoic. So this is from the Foster et al. 2017 compilation, which I should have acknowledged here. And now I take the carbon cycle models that I mentioned in the beginning that link all these carbon boxes, and I include explicitly rift length into these carbon cycle models in GeoCarbSolve. And so this is, okay, I start with previous data where people only used seafloor creation. So this is the original compilation, if you want, from Royer et al. 2014, which does not fit terribly well over the last 200 million years. It does better earlier on, but the last 200 million years, it's surprisingly bad, I would say. Then we take an update of this model where Royer says I changed this parameter that defines the efficiency of angiosperms versus gymnosperms. So this is the change that you get. You can increase your curve and get to a higher CO2 level in the Mesozoic. Then Vandermeer, this is what Sabine showed before, they looked at subduction length. And even though this is a questionable proxy for the amount of CO2 that is released due to subduction, I plotted it here, and I get a similar result, a high in the Mesozoic. And then I used rift length, and I get a Mesozoic CO2 high and a Cenozoic CO2 high. I don't claim that this fit is super great, but at least qualitatively, we have a high here, a low here, and a high here. And this is, again, I only look at rifts there, and I neglect all the other components of the carbon cycle, which is a super oversimplification. So of course, we have to account for all these other components as well. And I do that here in a very simplified way again, because this is just the way how we have to do it. So this is the length of the mid-ocean ridges over time. This is the length of subduction zones over time, all averaged in 10 million year intervals. So the gray one is from Vandermeer, the green one is from Vandermeer, the gray one is from Müller et al. 2016. So this is where Sabine's study was fed into. Then we have continental arcs, and we have large igneous provinces. And of course, these have to be all integrated with each other, but how they can be integrated is actually not so obvious. So what I did here, there's one slide missing. So if I say that all of these components have the same CO2 output, so that every kilometer of subduction zone has the same output as the rift, the same impact, then we get to an averaging of the curve and essentially to a mix of these curves that shows still a Mesozoic CO2 high, a low here, and a Cenozoic CO2 high over there. Okay, now this means that, well, this first of all means that rifts are previously underrepresented component of the carbon cycle. But this also means that we just need to improve. We have to do better in quantifying how much CO2 is released at all these boundaries. And there I like this study by Kevin Wong that Sabine also mentioned before, because he dared to put error bars on the data. And so this is mid-ocean ridges with a present day value of 77 plus minus 48. And this red line is reconstruction of mid-ocean ridge length through time. And this gray, this light red part, this is the error bar from present day, just taken backwards in time. And you see already that there is a huge error bar. Even at present day, there's a huge error bar. And then when going back in time, it is, well, discussable whether the error bar is not actually getting even larger than that, because there's uncertainty with reconstructing mid-ocean ridges to a time where there's virtually no seafloor preserved to present day. This is arc carbon flux, again, huge error bars. This is just the main message from these pictures, that the uncertainties are almost larger than the signal themselves. And this is continental rifts where the uncertainties are even higher. And so, well, think that if you would not have this red line in here and you would just have a point cloud that is filling up in some random distribution, this light red area, and you have to fit something to it, you could fit anything to it. So it's really, in the end, it's only a qualitative argument that we can make here and give future research directions. So one of these future research directions would be to dig deeper, to further, to go beyond rift length, to go towards evolution of rifts and what's actually happening in there, and not just a very oversimplified representation of that. And so this is what I'm trying to hint at in the last slides here. So if more CO2 is released during rifting, for instance, this is one question that one could address. Then what happens if a rift is turned into a seafloor spreading, into a mid-ocean ridge? So how, if we zoom into this transition? And this was done in Foley and Fisher in a nice review, where they argued that the continental lithosphere is a much larger store of carbon than the asthenosphere. And this is because carbon-rich melts can infiltrate, especially large parts of the lithosphere. And so one would expect that there is a high sea content at the base of, for instance, of cratons. And if we have now cratons breaking up, either by plume arrival here that starts to melt these carbon-rich places, or by continental rifting that is also just destroying the substance of the lithosphere, then this carbon will be released. It is prone to go into the melt first, and then the melt will transport it to shallow depth, where it can be released along volcanoes or along the faults. And this is what we actually see in East Africa. So coming back to this beautiful image of East Africa, where we have the distribution of carbon-rich volcanic rocks, carbonatites here at the edge of the craton, melilitites and nephelinites at the sides of the rifts. And then when the asthenosphere melting kicks in, we get these basalts in the center of the rift. So this is a snapshot of present day, but it can be seen as the result of continental rifting through time, where we form these volcanic features here first, and the basalts at the base afterwards, just during this basin-ward localization of rifting that I showed in the beginning. And this explains this distribution of these volcanic species along the rift. And this gives us a hint of how all rifts would have evolved through time, that we get more carbon-rich melts first and more carbon release in the beginning. But later on, if we progress with the rift, we will expect less CO2 released to the atmosphere. And so what we need to do next to just reduce the error bars, which sounds somehow boring, but this is the essential thing of getting any further in this type of business. We have to reduce the error bars. And so there I'm working on, well, getting a handle on the spatial and temporal variability of CO2 fluxes and rifts, getting better regional estimates, perhaps by linking airborne and ground measurements, because these ground measurements are very labor intensive. Carrying the accumulation chamber around, it would be perfect if there was a way of measuring CO2 fluxes from the air, and we are working on that with drones and airplanes right now. And what would help in terms of deep time reconstruction is a better characterization of present day CO2 fluxes in terms of magmatic activity, of rift velocity, of lithospheric age. So things that we can identify also in reconstructions and parameterize, and then feed into the carbon cycle models. So this is one of the drones that we just acquired at GFZ very recently, and we are going to test whether it's possible to measure CO2 fluxes with micrometeorological techniques that come from a large area. And just measuring larger areas would be a huge help in quantifying total fluxes. In terms of deep time reconstructions, better representation of all sources and sinks is needed. And the group in Sydney is working on that. Other groups are working on that. Mid-ocean ridges, young ocean floors, subduction zones of ophiolites. So many of the things that Sabine mentioned before. And in terms of the rifts, we would need much better definition of the evolution of the rifts so that we can understand better what CO2, how much CO2 is released during which period in time. So to summarize, rifts are prone to release deep CO2. This is related to the positive feedback between faults, fluids, and volatiles. Rift length correlates to some degree with the global Paleo's CO2 record, which gives an indication that rifts might have a much stronger role in CO2 release than was previously thought. And the future challenge is to reduce these ugly uncertainties and bring them to a level where we can actually start interpreting the small wiggles and the temporal evolution of individual components of the carbon cycle. And with that, I'd like to finish and thank you for your attention. I'm happy to answer questions.
Thanks, Sascha. Any questions for Sascha? Sascha, I would have a question. So also Sabine mentioned, also you mentioned the uncertainties, how important this is. Maybe it's a general question. How important is when you're doing the modeling, the error bar? When do you say, okay, this model is not good due to the error, or it's good? Because we've seen that the error bar is quite large. How do you...
You mean in the plate tectonic reconstructions, how you can quantify
or in the model in general? So you said in the slide that there's the error bar, for example, for the plate reconstruction, or for the model, or for the CO2 degassing. When do you say, okay, this model is okay? Which is the maximum error that you take, let's say quantitatively, that the model would work or not? I don't know.
Yeah, I think this is a complicated question because it depends on the region that you're looking at. So for all these global plate reconstructions, they are essentially stitched together from regional reconstructions. Mm-hmm. And every regional reconstruction is built on the available data that you have in this particular region. So it's not even easy to give uncertainties for global values, because they actually have to be broken down to regional values and regional uncertainties. And this makes this uncertainty business so complex and difficult. In particular, in plate reconstructions, where you have only one reconstruction, it's not so easy to give uncertainties. One way out would be to build reconstructions in an automated way, where you take all your observations as quantifiable inputs, and then you run a more computationally expensive way of building reconstructions, and to minimize some of your misfits to the data. And this is, I know that in Sydney, they've started this business with Proterozoic reconstructions, but doing this for all the data that are out there, I think this will be it's still far out. Sabine, what do you think?
Yeah, I totally agree, right? I agree with your approach that you essentially need to throw all the geological data you have at it. And you don't have to do that inversion. I mean, you could just apply to the forward models and see how consistent or inconsistent they are with the given plate reconstruction. But you still don't get away from some of the basics, like you run out of seafloor to use, you know, half of the world becomes unconstrained before Pangea, for example, right? So, you know, I think we just have to accept some level of uncertainty at different times. But yeah, certainly a lot more work required.
Can I make a question?
Yeah,
Sure.
Hi to everybody, and very nice talks. I'm sorry for Sabine because for problem of time delay, I could not attend your talk just from the beginning. But so, just a curiosity, a question for Sascha. So if most of the reconstruction and modeling are based on the length of these features, like the length of the rift zone or the length of the subduction zone, and how they evolve during time. But how do you think, how much could be important the variability along the length of the production, for example? I imagine that for this maybe less dramatic for rift system, but for subduction zones, the fluxes of carbon may be different from different geological sector or subduction zone that could depend on the amount carbon is subducted and many other parameters. So do you have this feeling how just simply how much the variability along the length? So maybe just the length could be limiting the possibility for modeling.
Yeah. So definitely, this is a good question. It was partially answered by Sabine before you arrived, where he compared subduction length and subduction volume reconstructions. Subduction volume would be the parameter that you might want to look at when you think that the melts are coming from the subducted mantle lithosphere. There's a huge difference between length and volume. In that case, I think it was area. And there was a study by Medicine East in 2019 that Sabine referred to. Maybe you can look it up in the record.
I'm sorry.
No, that's good. And then this is one way forward of making it a three-dimensional thing and not a length thing. Yeah, not as simple as length. For rifts, I think the impact is a bit less obvious because rifts are much slower than most of the other plate boundaries. So in East Africa, we have in Kenya, there's 2 millimeters per year extension rate. So this is an order of magnitude smaller than subduction fluxes that you have there. But of course, there's a change in the kinematics of the rifts. They usually start slow and then they become faster during seafloor spreading or right before seafloor spreading when they lose all their strength. And then, of course, more melting comes in, more CO2 might be sourced from depth. So this is the next thing that one would have to look at. I fully agree that the velocity has a big impact on the amount of melts and potentially also on the amount of CO2 release.
Okay, thank you.
I've got a follow-up question, if that's okay.
Sorry?
Yeah. I've got a follow-up question. So just to also reiterate, Carlo, yeah, the subduction zone lengths were not very useful for us. We had to look at the convergence rates in the subducting plate areas. And I think you make an important point. And so also for rifts, you know, I mean, at least the rift area might be interesting. Don't we have wide versus narrow rifts as well? And the velocities change even along a single rift. I think for me, one of the big questions is, you know, we've got the East African rift at the moment. And, you know, if we believe this extrapolated data, it has the same carbon output as all of the mid-ocean ridges on the globe combined. But the question is, what about other rifts? You know, when we think of Baikal, it's more of a passive rift. There's no mantle plume beneath it. Or what about the presence or absence of cratons, and therefore how much carbon you may have actually stored in the lithosphere? So I'm curious if you've thought about extending this analysis that way.
Paul, yeah, this would be great to extend the analysis. What right now, or what I've been basing this paper on, was the regional scale estimates that were available at that time. And there I found 4 different areas where people dared to give a regional estimate, because you have to dare it, because it's always based on small scale measurements that have to be extrapolated to an area. And one area was East Africa, where they had extremely high fluxes. Another area is the Ega Rift in the Czech Republic, where they have an order of magnitude less fluxes, but they also accounted only for more FETs for focused CO2 release settings when they computed their regional estimate. Another area is central Italy, where Carlo is the expert, and they found higher rates than in Ega, but not as high as in East Africa. And the 4th area was the Taupo volcanic zone. This is also a study that has been done a long time ago, Subert and Carrick, where they also extrapolate on regional scale. They vary by an order of magnitude, but they agree in the fact that they say there's a lot of CO2 coming out of the rifts. And in the study here, I accounted for that by having 2 scale features. Yeah? An average of these 4 regional estimates, and then a more conservative, like smaller value. But in fact, we don't know very well how the individual rift types, how the velocities, how the subsurface, maybe the carbonates that are in the area, how they interact with the volatile release. And this brings it down to that we need much more data for present day to quantify better why we have CO2 fluxes in these areas at that magnitude and not in other places.
Can I just make an additional comment? I think it goes back to the uncertainties. So the stomatal leaf densities, I like you say, it's just fascinating. It's incredible. But the issue is the experts in that field tell me the same thing about the atmospheric CO2 curves, that the errors are huge. And coming from a tectonics background, the paleoaltimetry constraints are atrocious in most cases. The best estimates for the Tibetan plateau 40 million years ago is 3 kilometers plus or minus 3 kilometers, right? So there's some grains of salt in even the paleo CO2 curves, and depending on which paleo CO2 curves that are used. But I mean, Sascha, you did mention it's more about the trends, and I think the trends are more robust.
Yeah, I think I fully agree. The way out would be not to try to go into deep time right away, but maybe be more modest and start with tens of millions of years. If that's deep enough. So that's a time scale that is where we have a lot of seafloor, where we can do really very well reconstructions, where the different CO2, paleo CO2 proxies, where they all converge, and work on this period better. Maybe go back to 50 million years, maybe to 100, but and then compare to the records that have smaller uncertainties with methods that have smaller uncertainties, and do that task before going further back in time.
Any other comments for Sascha or questions?
I just wanted to say I agree with that, Sascha. Except that often when we're looking at climate change, we want to capture several or at least one icehouse greenhouse state. So, you know, that essentially means we have to consider going back to, say, Pangaea. But of course, there's efforts to go back to 1 billion years and beyond. But you're right, like we have to just do it in a guarded and very careful manner.
Yeah, I like the deep time reconstructions. Yeah, they also make you fantasize about what's possible. But it's maybe we can agree on that we have to do both. Yeah, the ones with high uncertainties and the ones that are more prone to reduce the uncertainties, and then we get truth out of converging both of them.
Thank you, Sascha. So a big thanks to Sascha and Sabine for the 2 nice presentations. A good insight on the tectonic part. So thanks again, and see you or the others next week.
Okay. Take care, everyone. Thanks for your time. Bye-bye.